Now, one can have more complicated circuits. So, the method actually is useful only for more complicated circuits. So, if I have on the DC side something other than a current source, then it becomes more complicated. Now, let us look at one circuit which is actually more complicated than the circuits we have seen so far. So, the circuit I am considering now is on the AC side, I have a 3 phase balanced voltage source. In each phase there is a resistance and an inductance. Valves 1, 3, 5, valves 4, 6, 2. Now, on the DC side, we consider a model consisting of a resistor, an inductor and a voltage source, a DC voltage source. So, VD is the voltage across this voltage source, R D is the resistance, LD is the inductance. So, we have the same expressions for EA, EB, EC, which we have been using, root 2 by 3 V sine omega OT plus 150 degrees. EB is root 2 by 3 V sine omega OT plus 30 degrees, and EC is root 2 by 3 V sine omega OT minus 90 degrees. So, if I want to analyze this circuit, so I can employ the general steady state analysis. So, let us try to do the steady state analysis. So, essentially finding x 1, x 2, a 1, u 1, a 2, u 2, f g. So, let us start with 2 and 3 valve conduction mode. So, if I take 2 and 3 valve conduction mode, so if I take the first subinterval, so there are 3 valves conducting in the first subinterval. So, I will show only those valves that conduct current. So, the equivalent circuit is like this. This is valve 1, valve 3 and valve 2. So, this is ID, oh sorry, we have a different circuit now on the DC side. So, I have a resistance, inductance and a voltage source. So, this is RD, LD, VD. So, how many elements are there in the state vector x 1? This is unlike the previous circuits where there was a constant current on the DC side. So, there is no longer a constant current. So, if I consider the current, the instantaneous current ID, it is not necessarily a constant. So, we can't actually ignore this loop while I mean we have to include this loop consisting of RD, LD, VD also in the equations. So, if I take x 1, then what are the elements of x 1? So, there are two loops. So, there should be two elements. The first element is ID and the second element is nothing but the current in the outgoing valve. The current in the outgoing valve is nothing but I 1, valve 1 is the outgoing valve. So, ID and I 1 are the elements of x 1. So, let us try to write the equations for the circuit by applying Kirchhoff's voltage law, and once we bring it to the standard form we can get A 1 and U 1. So, if I take the loop consisting of EA, EB, R and L in series with EA, R and L in series with EB and valves 1 and 3, then I have by Kirchhoff's voltage law EA minus EB is equal to R I 1 plus L d I 1 by dt. So, if I take the current here, this is ID minus I 1. Minus R ID minus I 1 minus L d by dt of ID minus I 1. If I take the loop consisting of EB, EC, R and L in series with EB, R and L in series with EC, the valves 3, 2, RD, LD, VD. So, if I take this loop and apply Kirchhoff's voltage law, I get EB minus EC is equal to R into ID minus I 1 plus L d by dt of ID minus I 1 plus RD ID plus LD dID by dt plus VD, and the current through valve 2 R and L in series with EC is nothing but ID plus RID plus L dID by dt. So, these are the two equations. So, we can write these equations in the standard form. So, I will write this as a equation in the vector matrix form. So, I will take the terms involving the derivative of the state variables. So, dID by dt, dI1 by dt. So, let me first consider the terms involving dID by dt and dI1 by dt in these two equations. So, in the first equation, if I take the coefficient of dID by dt, so there is a L dId by dt with a negative sign. So, minus L dId by dt, and if I look at the coefficient of di1 by dt, so there are two terms involved, I mean two times L di by dt is appearing twice. So, 2L is the coefficient of di1 by dt. If I look at the second equation, the coefficient of dId by dt, so I have L dId by dt plus Ld dId by dt plus L dId by dt. So, it is 2L plus Ld. So, 2L plus Ld is the coefficient of dId by dt. Then the coefficient of di1 by dt is minus L. So, I will equate this to the remaining terms on the other side. So, first I will take the terms involving Id and I6. So, in the first equation, the coefficient of Id is R, the coefficient of I6 is the coefficient of this is I1. So, the coefficient of I1 in the first equation is minus 2R. In the second equation, the coefficient of Id is 2R plus Rd with a negative sign. So, it is minus 2R minus Rd, and the coefficient of I1 is R. Then there are other terms in both equations. So, in the first equation I have Ea minus Eb. In the second equation I have Eb minus Ec minus Vd. So, if I pre-multiply this equation by the inverse of this square matrix on the left hand side, I get the equation in the standard form. So, from that I can get A1 and U1. So, I can write A1 as minus L 2L 2L plus Ld minus L inverse R minus 2R minus 2R minus Rd R. So, this is A1, and U1 is minus L 2L 2L plus Ld minus L inverse Ea minus Eb, Eb minus Ec minus Vd.